So Euler's formula. Let's start by looking at these things called Maclaurin series. Basically, it represents a function as an infinite sum. You see, all of our functions can be approximated with a polynomial. That's why we spend so much time investigating polynomials. They're quite important functions. So e to the power of x is actually defined here with its Maclaurin series. And you can see there's the general term, x to the power of n over n factorial. Now if you took the infinite sum of that, then that would actually be the same as e to the power of x. And there's a graph just to demonstrate. So the black one is e to the x. The blue one is 1, what did I go up to? There you go, I went up to x cubed over 3 factorial. So I've only put the first 4 terms in, and you can see it's already starting to wrap around the exponential. The fun thing is to get on Desmos. Well, okay, it's my idea of fun. And you put e to the power of x on there, and then you just keep adding the extra terms, and you watch the blue curve start wrapping around and around the exponential, and it gets closer and closer. So there's the definition for e to the power of x. Cosine x is this one. So you've got minus 1 to the power of n, so the signs are alternating, plus minus, and it's x to the power of 2n, so all the even powers over the 2n factorial. So there's the cosine curve, and then the blue one, again, I just put in the first 4 terms there. That one's even more fun on Desmos when you see it rapid, because it goes down and up and down and up, and it's great. Sine are all the odd powers, and again, they're alternating, you'll notice. So there's our sine curve, and the blue one, first 4 terms, and it's quite good around 0. You don't need a lot of terms, so all of them you might have noticed, I was going to say you would have noticed, all of them around 0, it's quite good. So for small values of x, really good. So that brings us to Euler's formula then. So Euler's formula does this. It gets imaginary numbers, and it converts between the exponentials and the trigs. And technically it's doing it via the polynomial. So if we let x equals theta in that Maclaurin series for cosine and sine, so there they are. So cosine, the even powers, sine, the odd powers. If we let x equal I theta, we would get this expression, 1 plus I theta squared on 2 factorial, I theta cubed on 3 factorial, and so on, and so on, and so on. I could rewrite that because I squared is negative. I to the power of 4 would become positive. I to the power of 6, it's not there, would be negative, and so on, which means you could rewrite it like this. And there's the definition for sine theta and cosine theta. And that's how we get the cos theta plus I sine theta. So that's how you'd prove it. Well, no, it's not how you'd prove it, because as I say, the infinite series is not actually in the course. But that's how we can prove that e to the iota theta is in fact the same as cos theta plus I sine theta. So that is Euler's formula. E to the iota theta is cos theta plus I sine theta. And that will always be true. This now gives us a third way of writing complex numbers. We know z is x plus iy. Well, that's Cartesian form. So x and y being the Cartesian coordinates, sometimes called component form as well, because in vectors we would call it component form. We then saw that's the same as r cos theta plus I sine theta. That's known as polar form. Also mod arg form is the other word we use for it. But if they ever say polar form, that's the form they're talking about. But now we can also write it as re to the iota theta, and that's exponential form. So they're the 3 forms that we could write a complex number in. So if we had to write 4 minus 4i in exponential form, we've still got to work out the modulus and the argument. So mod arg form, we saw it before, I think it was one of our previous examples, 4 root 2 cis minus pi on 4, so it becomes 4 root 2 e to the power of minus I pi on 4. We can use it to multiply and divide complex numbers then. So z is root 3 plus I, w is 1 minus root 3i. Find z times w. If I convert it into mod arg form, well, I've gone straight to exponential form. Okay, if I convert it into exponential form, then we just use our index laws. And this also explains why when we're multiplying, we add the arguments. Because in index form, of course, that's exactly what we do. We add the powers. So we get 4e to the minus I pi on 6, which then I can convert back via the mod arg form, and we get 2 root 3 minus 2i as our answer. Z divided by w, well again we can use our index laws, and we get I pi on 6 minus I pi on 3, which becomes I pi on 2, so that would just be I. Z to the power of 5 becomes 2 to the power of 5, e to the 5i pi on 6. And again, we can convert that back via the mod arg form. We get minus 16 root 3 I. Okay, so that's just a start looking at the exponential form of a complex number.